Continue from our previous lesson. Do you remember what you have seen in our previous discussion by our Zoom class? Do you remember what you have seen? Yes? Do you remember what you have seen in our previous discussion? No one? Huh? No one? For example, in our previous time, we have seen about uniformly accelerated motion and the uniformly motion, okay? Uniformly accelerated motion is the motion of a body along a straight line with constant acceleration, okay? It is velocities changed in equal interval in equal time, In our today discussion, let us see free falling body and the graphical representation of uniform motion and the uniformly accelerated motion. Graphically, how we can represent uniform motion by graph and uniformly accelerated motion by graph. Okay, we will focus on this one in our today discussion. Before that, let us see free falling bodies. Free falling body is when we talk about free falling body, it is the example of uniformly accelerated motion. Okay, uniformly accelerated motion. It is the type of uniformly accelerated means it is acceleration is constant. And it is uniformly accelerated. Free falling bodies are which a body falls under the action of gravitational force. When gravitational force attracts a body, it's free fall to the earth. For free falling bodies, initial velocity is 0. Okay, for free falling body, because of its fall from the rest, it is initial velocity is equal to 0. Initial velocity is equal to 0, and the acceleration is equal to gravitational acceleration, which is equal to 9.8 meter per second square. Therefore, final velocity is equal to gravitational acceleration plus time. This one comes from what? For example, in our previous time, if you remember, final velocity is equal to acceleration times time plus initial velocity. Have you seen? In this case, we do have acceleration is equal to gravitational acceleration, and initial velocity is equal to 0. Therefore, gravitational acceleration times time plus initial velocity is equal to 0. Therefore, it gives for you GT, okay? It gives for you GT. In free falling body, for example, when you find the final velocity, you must use, instead of acceleration, gravitational acceleration, which is equal to 9.8, and its initial velocity is equal to 0. Therefore, you can use this equation in the equation of free falling body. Therefore, under this one, what you must know, what is free falling body is, it is acted by what, and they are the example of free falling bodies are the most example or the most common example of uniformly accelerated motion. Okay. So under this one, you must know it is equation. Let us see one example under this one. What is the speed of a ball dropped from a building after 3 seconds? After 3 seconds. Try this question, please. Try these questions. What is the speed of, visible or not? This question is visible for you. Visible?
Yes.
Okay, try. We will do together, okay? Try by yourself and we will do together. Mr. Mendino. Have you tried? For example, gravitational acceleration is constant 9.8 meter per second square, okay? Meter per second square. What is the speed of? That means the speed with a direction means it gives for you velocity. Don't forget this one very well. For example, in free falling body, it is because of occurred on a straight line or uniformly. Instead of speed, we can use or interchange speed and velocity. Don't forget everyone. Sorry. Have you tried? Let us see together. What is this answer? Huh? What's the answer of the given question? No one? Yes, yes.
$29.4 meter per second square.
29 meter per second square. Okay, meter per second square or meter per second? The required
Meter.
one is, by the way, meter per second. It can be. Let us see together, okay? The required one is final velocity, okay? As we have seen in above equation, final velocity of free falling body is equal to gravitational acceleration times time, okay? Gravitational acceleration times time. That means 9.8 meter per second square times 3 seconds, okay? 3 seconds. 1 second cancelled by 1 second. Have you seen? 8 times 3?
29.4 meter per second.
29.4.
Okay. It can be 4 and 2, I think. 2, 3 times 9, 27, 27 plus 2, 29, okay? 29.4 meter per second, okay? Meter per second, not meter per second square. Not meter per second square. Therefore, the speed of a ball dropped from a building after 3 seconds is 29.4 meter per second, okay? Meter per second. Therefore, under free falling body, you can use this equation, okay? You can use this equation in your such type of question, okay? In such type of question. The other point, representation of uniform motion and the uniformly accelerated motion using table and the graphs. In our previous time, if you remember, we have seen some of this motion we have seen using by table and some graphs. For example, in uniform motion, distance changes equally for equal interval of time, and speed is constant and the acceleration is 0. We have seen this one in our previous time, okay? We have seen this one. Keep in your mind this one, and let us see the graphical representation of uniform motion under uniform motion. Let us see the graphical, for example, displacement time graph, velocity time graph, and the acceleration time graph. For example, in displacement time graph, you can take this one or vertically displacement and horizontally time. Therefore, when we draw, it seems like this one, t in second, and this one is displacement in meter. So when you put on this one, when you put on this one, in uniform motion, it seems like this one, okay? It seems like this one, direct relation. So under this one, velocity is constant and the acceleration is zero, okay? Acceleration is zero. In such a type of equation, slope is equal to velocity, okay? Slope is equal to velocity. If you calculate the slope of velocity, for example, that means change of displacement over change of time, okay? We have seen this one in our previous time again. Therefore, under this one, displacement time graphs looks like this one, okay? Looks like this one. That means slope of the given graph is equal to velocity of the given quantity. And in uniform motion again, the graph of displacement time graph is looks like this one, okay? It looks like when we draw, it looks like this one. Maybe look. Have you seen? This one is time in second. This one is speed in meter per second. In such a type of graph, acceleration is zero, okay? Acceleration is zero. Therefore, area is equal to displacement. That means in velocity time graph, displacement is equal to area. That means area is equal to velocity times time. Displacement, for example, if you calculate from this one, your displacement, assume your initial velocity is zero. Displacement is equal to velocity times time. Velocity times time means it gives for you area. For example, if you see this one, it seems like what from what we have seen in our previous time. What type of this looks like? Triangle, rectangle, or triangle? What this one seems like?
Rectangle.
Okay. Rectangle, excellent. The area of rectangle is equal to it is length times it is width. On it is length, we do have time. On it is width, we do have velocity, okay? Therefore, area under velocity time graph in uniform motion gives for you displacement, okay? Displacement. Area in under velocity time graphs gives for you what? It is equal with what? Displacement, okay? Equal with displacement. For example, if you find for the first area of the given graph, it seems like some triangle. Therefore, you will apply the formula of triangle and you find it is area. Therefore, the area under this velocity time graphs gives for you displacement. Clear? When we represent by graphically uniform motion, we do have first, it seems like what we have seen in A, and then in B, velocity time graph of uniform motion, okay? Uniform motion. The third one, the third one is, for example, acceleration time graph. Do you remember what you have seen in our previous time? What's acceleration time graph? What acceleration time graph? Do you remember? What is the acceleration time graph of uniform motion? Acceleration is what? Acceleration is what? Yes? Acceleration is what? No? For example, in your vertical axis, because of acceleration is 0, it seems like this one, okay? There is no acceleration. There is no acceleration on uniform motion, okay? Because of what? Because acceleration is equal to acceleration is equal to 0. Because of what? Because of there is no change in velocity, okay? There is no change in
Velocity.
velocity. And uniform motion, because of velocity is constant, acceleration is equal to 0. Acceleration is equal to 0. That means there is no change in velocity. There is no change in velocity. Therefore, when we represent uniform motion, we can represent what we have seen, the graph of what we have seen in A, B, and the C, in A and the B and the C. Therefore, when we represent graphically uniform motion, it seems like this one, okay? It seems like this one. For example, we can see later, it can be given for you such type of, to find area of uniform motion. Area of uniform motion everywhere equal with displacement. Displacement of uniform motion is equal to velocity times time, okay? Times time. Don't forget this one. Don't forget, okay? Clear what you have seen? What you have seen is clear for you?
Yes.
Let us see uniformly accelerated motion, graphically how we can represent uniformly accelerated motion. Uniformly accelerated motion. Uniformly accelerated motion, this one is what we have seen in our previous time. Uniformly accelerated motion, distance does not change equally for equal interval of time for uniformly acceleration motion. And speed is equally changed for equal interval of time, okay? Speed is equally changed for equal interval of time. That means there is change in speed. There is change in speed and the acceleration is constant. Acceleration is constant. Therefore, we can represent this one by graph, okay? This one can be represented by graph. For example, velocity in meter per second or speed in meter per second in a certain direction, and the time in second. For uniformly accelerated motion, it seems like this one, okay? It seems like this one. Therefore, slope under this one, look, slope of this graph is equal to acceleration, okay? Slope of this graph is equal to acceleration. Slope of this graph is equal to acceleration. And in this case, we have seen velocity time graph, the area under this one is equal to displacement. It seems like what we have seen in our first in uniform motion. But in this case, uniform motion, when we talk about area, it is equal with change in velocity. Equal with change in velocity. For example, if you take this one as initial, 0, 2, 4, 6. If you calculate the acceleration of this one at every point, you will get 2 meters per second square. 2 meters per second square. And it is slope is equal to, because of acceleration and the slope is equal to the acceleration again 2 meters per second square. 2 meters per second square, okay? 2 meters per second square. For example, in above question, because of there is no slope in C, especially slope is equal to 0. Okay, slope is equal to 0. In case of this one, we do have acceleration and the slope is equal to the acceleration of the given graph. Okay, the acceleration is equal to the slope of the given graph. And what about the acceleration times time graph looks like in uniformly accelerated motion? In uniformly accelerated motion, what the graphs looks like? Yes, what the graphs looks like? This one is acceleration in meter per second square. This one is time in second. Maybe my graph maybe not straight. Think as straight. What it is, seems like, because of acceleration is constant at any time. At any time, acceleration looks like this one. Your acceleration is constant, okay? Your acceleration is constant. Your acceleration is constant. So what is the area of acceleration times time of times time graph in uniform motion? What is the area? Area is equal to, for example, have you seen this? The area of this
Velocity.
Displacement.
graph? Changing?
Area represents Z.
Yeah.
Change in velocity.
Thank you. Change in velocity. For example, look, area is equal to change in velocity or velocity. Change in velocity.
Velocity.
Change in velocity. Your velocity, have you seen this one? Velocity, for example, is equal to velocity is equal to acceleration times time. Assume your initial acceleration is 0. Your initial acceleration is 0. Therefore, change in velocity means acceleration times time. For example, if this one is around 6 seconds, and on this point we do have 3 meters per second square. What's your area, or what is your change in velocity? What is your change in velocity? Your area or your change in velocity? For example, assume acceleration is equal to 3 meters per second square, and time is equal to 6 seconds. Simply multiplication, okay?
18 meters per second.
30 per second.
Yeah. 18 meters per second. Therefore, the area under given such type of graph, or for example, acceleration times graph, is equal to what? Equal to change in velocity, okay? Change in velocity, change in velocity. Therefore, when we represent graphically uniform motion and the uniformly accelerated motion, you must consider it is, or you must know it is slope and it is area. It is area, especially in uniform motion. In uniform motion, the area of velocity time graph, the area of velocity time graph gives for you displacement, and in uniformly accelerated motion, the area of acceleration time graph gives for you change in velocity, okay? Change in velocity. If you understand this one, you can calculate slope, acceleration, area, velocity of uniform motion and the uniformly accelerated motion, okay? Uniform motion and the uniformly accelerated motion. Have you understand? Huh? Have you understand what you have seen?
Yes, Mister.
Yes.
Okay. Let us, depending on our time, let us give for you one question which we can calculate. It is area, again it is acceleration, as well as what type of it is motion. Let us see one question together. And what a whiteboard. So we will try on whiteboard and do it. Whiteboard. Okay, see, from this graph, from the graph, of velocity time shown, for example, look, this graph, maybe it is given for you by velocity meter per second and time in second. 0, must be somewhat long. T in second, velocity in meter per second. Let us start from 2, 4, 8, and 10. Okay. Is it visible for you, by the way? Visible?
Yes.
Okay.
Yes.
It is not comfortable for graph. Try for the best one. Okay. Try for the best one. 8 and up to 16. Okay. 16. When we see this one, this graph is looks like when it reach on 2 or somewhat it seems like this one, okay, even if it is not as much as okay. Have you seen the graph somewhat, even if it is not straight? Have you seen? For example, from the graph above, what is the acceleration during, what is the acceleration during the first 4 time? What is the acceleration? What is the acceleration? The acceleration during the first 4 seconds. 4 seconds. Have you seen? Why is the acceleration of this graph? Why is the acceleration of this graph during the first 4 seconds? This one is 16, I have said. This one is 16, okay? Not 10. 16. Why is the acceleration? This one is your velocity. What about this one? Your time. What is the acceleration of your acceleration during the first 4 seconds? The first 4 seconds.
4 meters per second.
How many? How many? 4 meter per? Yes?
Second square.
Second square. Look, acceleration is equal to change in velocity over time. What is change in velocity? I think 16, 16 meter per second over what is your time? 4 seconds. Is equal to
4 meters per second
meter
square.
per second square. Yeah, 4 meter per second square. B, what about after, for example, what about the acceleration after 4 seconds? What is the acceleration after after 4 seconds? What is the acceleration after 4 seconds? After 4 seconds, have you seen what it seems like your graph? For example, this one is 16 minus 0. What about after 0? After 4 seconds? For example, when your time is 4, what's your velocity? 16. And when your time reach on 10 seconds, what about your velocity again? Huh?
60 meters per second.
62. Therefore, the acceleration is what? The acceleration is what?
2 meters.
Huh? Are you sure? Are you sure? After 4 seconds, the acceleration is equal to 0. Why for? Acceleration is equal to 0. Why? There is no change. Is there change of velocity between 4 up to 10? Is there change of velocity? Huh? Is there change of velocity? There is no change of velocity between after 4 seconds. The velocity is constant. Okay, the velocity is constant. If the velocity is constant, the acceleration become 0. The acceleration become 0 because of what? Because of there is no change in velocity. Okay, there is no change in velocity. There is no change in velocity. Have you understand? Have you understood what we have said?
Yes.
There is no change in velocity after 4 seconds. Okay. What is the type of motion during the first 4 seconds? What is the type of this motion? For example, 0 up to 4 during 4 seconds. What is this type of motion shows?
Uniformly
What it shows?
accelerated motion.
Uniformly accelerated motion. Okay. Uniformly accelerated motion. During for example, I'd see, for example, during the type of motion during 4 seconds is uniformly accelerated motion. Okay, thank you. Uniformly accelerated motion. What about after 4? After
Uniform
4
motion.
seconds? Uniform motion. The type of motion, the type of motion after 4 seconds is uniform motion. Okay, uniform motion. So you can see and you can decide it what type of motion from the given graph. Okay, from the given graph. Okay, another question. Let us ask you: how far does the body moves in 4 seconds? How far does a body moves in 4 seconds? How far does? How far means, do you know? How far? What is how far does the body moves mean? Do you know? For example, in 4 seconds, how far does the body moves in 4 seconds? Have you seen the graph? In 4 seconds?
64.
What?
64 meters.
64 meter, it can be, but what it seems like, do you know the area or area G of this graph is equal to displacement? Okay, how far means displacement q or distance q. Have you understand? But what your graph seems like, your graph up to 4 seconds, this triangle, okay, triangle or not? Triangle. Therefore, look, Therefore, in E, for example, if you continue E, how far does the body moves? The body moves in 4 seconds. In 4 seconds. In 4 seconds. To calculate this one, distance or distance of the given graph is equal to area. Okay, area. This area seems like, because of a triangle, you must apply the formula of triangle what you have seen in our previous time. The area of triangle is equal to what? Half or 1/2 base times area. It is basis, width is velocity, and it is length is time. Therefore, multiply and divide by 2. For example, 1/2 times 16 meter per second times how many? 4 seconds. 1 second cancelled by 1 second. 1 second cancelled by 1 second. By 2, 1 by 2, 8. 8 meter times 4. How many? 8 times 4. How many? 32. 32 meter. So you forgot 62 divided by 2. Okay, the first your answer was this one. Okay. Have you seen how we can calculate the area? The area or the displacement of the given graph? Yes? Huh?
Yes.
Okay, for example, try this one by yourself, okay? And we can do in next break. For example, how far the body moves? The body moves in 10 seconds. In 10 seconds. As hints, let us give for you hints. For example, this graph is in the first one, you do have area one, what we have calculate now, and area 2, okay, area 2. The addition of area 2 and the area 1 is gives for you the distance or the far the body moves in 10 seconds. That means this one is 32, and find for area 2. Area 2 is equal to 1, 2, and divide times by 16. Divide by, not divide because of it seems like rectangle, and add, you will get the total displacement. Okay, the total displacement on this one. Try by yourself, and if it is not clear for you, we will do together next period. Okay, for today enough for us.
Sir,
You must, yes,
Mr.
yes.
ፈተና ጌት ነው የሚመጣው።
ይቆራረጣል።
ይሄን ያጠቃልላል እንደ ሚስተር
ምን እያልክ ነው? ምን አላችሁ?
ፈተና ጌት ነው የሚመጣው።
ዩኒፎርም ሞሽን እና ዩኒፎርም አክሰለሬት ሞሽንን ያጠቃልላል። እሺ፣ ስለዚህ ይሄኛው የሚገባበታል ማለት እሺ፣ ሊገባ ይችላል እና አንብቡ። ለማንኛውም እንደዚህ በግራፍ ችግር የለም። እስኪ
ከስንት ነው የሚመጣው?
ከስንት ነው? ጥያቄው 15 ነው። ከ10 ነው መሰለኝ። እሺ ሚስተር። እሺ ጉድባይ። enough for today, okay?
Bye.
Bye.
Bye, Mr.